Okay, welcome back again. So what we have seen in the last two sessions is, we'll talk about a little bit what distributions are and arriving at base theorem. In the last session, we were talking about sampling methods, looking at metropolis sampling, metropolis hastings, and then eventually Gibbs sampling. And what we want to do now is try to show you how we actually use this in practice for real CMB experiments and the cases that we are interested in. So what I'm talking about now is, let's call this something like the BeyondPlanck, or so that's the past, and then Cosmoglobe, the future, Cosmoglobe, Gibbs sampler, or let's call it data model. And as Ingun has already explained, the goal of what we're trying to do here is to model both the cosmology and astrophysics and the instrumentation in one go. So what I want to do now is to try to write down a data model, D, that contains all the relevant parameters that we are interested in a form that allows us to actually work with it and sample it and work with it. And so let's start simple and try to build it up gradually. And the first thing we want to do is, okay, let's assume for now that the data consists of true signal coming through from the sky. So let's call that something like SCMB. This is a really ideal experiment where the detectors only are sensitive to CMB photons. Can happen in practice, of course, but let's assume that for now. SCMB plus noise, and let's also, for simplicity, assume that the noise is what we call white noise. It's uncorrelated between any two samples in time. This would be a fantastic world to be in, except that none of us would have jobs if this was the case. It would be trivial and it wouldn't be any challenge. Fortunately for us, to get funded, the life is more complicated than that. So first of all, let's talk a little bit about what the CMB, how to parameterize the CMB. And let's think about what a CMB map looks like. It is something like this, and it may have some hot spots here, it may have some cold spots here, and perhaps a hot spot over here. And the point is that whenever you point your telescope towards one of those positions, you will get a value that is slightly higher or slightly lower than the average. Slightly fewer photons will hit your detector if you point it towards a cold part of the sky. But now, so it has some spatial distribution depending on position. And that's really what you want to know, of course. But the other thing about the CMB is that it has a frequency dependence. So if I'm plotting now, let's do it up here because we need to carry it on while we go along. So I'm going to say this also up here for frequency, nu in say gigahertz, versus, let's call it SO nu. So that is the strength of a given astrophysical plot as a function of frequency. And the CMB, the way we calibrate the data, the CMB is typically flat. So here is CMB. Independently of which frequency you are observing in, you always get the same value, and that's what's called thermodynamic units. For practical purposes, it's more convenient to work with what's called Rayleigh-Jeans units. And if you do that, there's another factor that pops in that makes it curve down around 300 gigahertz. It looks something like this. But the point is, this is a very precisely known analytical function. We know what it looks like. Only depends on the CMB temperature of 2.7 Kelvin. It's very, very well known. So now we know exactly how this behaves in frequency. So if we're observing at 30 gigahertz here, for instance, we know what it is, or 100, or 353 gigahertz, or whatever. We know how strong they should be relative to each other based on analytical knowledge about the CMB. And that's really all we need to know. The frequency dependence, and then we're going to try to fit the spatial dependency after the fact. However, this isn't the only component that is available on the sky. For instance, we have, say, S synchrotron, Or we have, say, S dust. Or we have spinning dust. Or we have S, let's think about CO, whatever. So if we just plot that in the same plot, here perhaps you have synchrotron. So this is sync. Here we have thermal dust. Here I have AME. CO is perhaps over here. And so on. I mean, it's a populated place. Our own galaxy, there's a lot of emission mechanisms that happens there. And now it's starting to get interesting, because these things here are not that well known. For instance, the synchrotron, we don't know if this thing here pulls a frequency this fast or this fast. So that is a new parameter that needs to be fitted. And so we need to replace this simple model here with something that is slightly more complicated. And what to do is, okay, let's define this at some reference frequency. So perhaps we measure synchrotron at 30 gigahertz. In that case, let's say that S is exactly what is this amplitude here at 30 gigahertz. But then we need to parameterize this function here, which is called a spectral energy density, or SED, by something. And this is a logarithmic plot, so this is log units. And normally what we say is that this thing here is defined as nu divided by nu ref to some power alpha or beta. And so we now have two parameters to fit for in terms of the synchrotron. It's the amplitude and its spectral index. And we want to fit both of those as part of our parametric model. For dust, it's even more complicated. In that case, this shape over here, that is often what is called a modified blackbody. And it has a shape that looks something like proportional to nu to beta plus 1 divided by E h nu over KT plus 1. It's minus 1. I'm getting confused right now. And there are two parameters here. It's beta and a temperature. So this is essentially like a black body, but it's tilted by this factor here. And so we have some parametric function here, but let's call that just S F dust, for instance. And in that case, we get an F dust in there that depends on beta dust and temperature. And each of these other parameters, components here as well, have some parametric function that we may want to try to fit. After a while, this gets really messy. And so rather than carrying around a whole bunch of these terms individually, what we do is to introduce a general frequency label over there, and then say that, okay, we introduce something that is called a mixing matrix. Mixing matrix. And that is simply define M, and let's call it nu comma C, where C is component. So component here can be CMB or synchrotron dust, while nu is the frequency. And this matrix here simply tells you how strong is each of these components as a function of frequency and components. And let's just symbolically call the three parameters there beta. So it looks something like this. Here I have CMB, here I have synchrotron, here I have dust, and so on. And here I have 30 gigahertz, here I have 44 for Planck, 70, and so on until 857. And what does it look like? Well, CMB equally strong in each channel, so that's just 1, 1, 1, 1, 1. Synchrotron is defined to be 1 at 30 gigahertz, and then falls as you go along, so perhaps 0.7, 0.2, 0.05, and so on. Dust is strong, so if it's 7, it's usually we reference something like that, 1 there, and then it may be 0.86, 0.5, 0.43, and so on. 31, as given by this function here, for each of the other frequencies. So essentially what this mixing matrix does is tell you how strong is a given channel at each frequency, or a component at each frequency. And if we do that now, we can actually replace this whole line of different components here with a much more convenient expression that simply looks like M, C nu, and then some general amplitude vector AC. So now this is, think about this as the sky map of component AC. So one of these is just the C and B. So A is now a stacked vector of A, C, and B for each of the pixels, A sync for each of the pixels, A dust, and so on. And that means that this thing here, and if I now additionally sum over C, this is the total sky signal coming from the sky at frequency nu. Sum over all of them. So this is a mathematical convenient form to write this in. So that's what we will be using. If you now want to add a new component to Commander, that is essentially the same as adding another column to this matrix and define how does this depend on frequency. That's the main part of that. So let's get rid of that. So now we have a nice representation of the sky that depends on the sky, on some set of spectral parameters, beta, and this is now the set of all of those spectral parameters describing how each of these vary. And then a C, so the CB map is in here, the signal map is in here. This is the spectral behavior, unknown, unknown. This is a mathematical relation. Okay, so now we have a model for the sky. The problem is this isn't all we got. If you think about the detection chain, so to speak, the first thing that the photons see as they come along into our instrument is the telescope, essentially, the telescope dish. And the photons are being captured here. And that is what we call, the effect of that is called an instrumental beam. So let's call that something like B over nu. Yeah, which is, think about this as a matrix as well. And if you think about in 1D what it means, suppose you have a 1D signal that this is a sky signal that is at infinite resolution, so to speak. So here we have position X, and here is the signal strength, S of X. What the beam does is it smooths out the signal. So the larger the telescope, the more fine details you can see, but all of them will have some finite resolution. So imagine that the beam size of our instrument is something like this. It's a Gaussian with some width. Well, then the resulting signal is going to look like a smooth version of the underlying signal with this as a smoothing scale. So what you'll be reading off is something like this. This is what the true sky signal is going to look like. It's a smooth version of the underlying feature. And it's important to know this thing here because if you want to estimate what the true sky is, the true CB, then essentially you have to be able to take into account how strong is the smoothing at different scales and try to do what we call deconvolution. You have to deconvolve the beam here. So that is a big part of the data model. The beam is important. So here we have a beam. This thing here is sky signal. Okay, but if we now turn to something called a bandpass, a detector, that any detector is not sensitive to all frequencies or just a single sharp frequency. Rather, it has a sensitivity as a function of frequency. So nu here, and it may look something like this. This is what we call a bandpass. So let's call it tau. Tau is the usual function that we use. So here, it has a value of 1, for instance. And it says that at this frequency, which may be 30 gigahertz, it's maximally sensitive. And then it drops down to say 26 gigahertz here and perhaps 34 gigahertz there. and this sort of defines the sensitivity range in frequency space. And what we then have to do to take into account the bandpass or sensitivity as a function of frequency is essentially to integrate this thing here over the bandpass as well. The nu, and we integrate over tau of nu, the nu. So now I have this thing here and a C. So in practice, we usually redefine the bandpasses such that this thing here just becomes part of that. And we'll use that, do that for notation as well, for simplicity. And forget about this thing here, and just remember that the mixed matrix itself actually contains a bandpass element as well. So I'm going to write it here, bandpass. And that is again uncertain. You don't, when you're doing the measurements on the ground, this is very, very hard to actually measure the sensitivity, and it changes when you launch it in space, so you don't know exactly what the shape is. And it may be something like this instead, or something like that. And so there are certain parameters here as well that need to be estimated, and we often call those delta bandpass. So that's another degree of freedom that we need to estimate jointly from the data. That's not all. So when the photons have come through the detector chain, it's hitting through the telescope chain, it's hitting a detector. It's being captured by some form of amplifier, more typically, and that is describing what is called a gain. So think about that as some machine that amplifies the signal from just a tiny, tiny amount of the energy in a photon to something that can be detected by a recording device. And we need to typically multiply it by, say, 6 or 10 orders of magnitude. So it's a huge boost factor. The problem is that these detectors are not stable, or these amplifiers are not stable. So this now also will depend on timing. Yeah. Actually, let's hold off the game. I'm getting ahead of myself. Okay, so now we have photons coming from the sky, going through a bandpass, being seen by optics. But then there is something called a pointing matrix. So at any given time, a CAD experiment is pointing towards some position on the sky. And then at the next time, it's moving here, and then there, and then there, and then there, and then there. And so we introduce what is called a pointing matrix. And we also denote P, and then it has two indices, T and P. And P corresponds to which pixel am I seeing at any given time. So this thing here has a very, very simple structure. Here is pixel on the sky. So that corresponds to which position am I pointing at. And then here is time. And for any given time, you're only looking at one pixel. So this is going to look like 0, 0, 0, 1, 0, 0, 0, 0, 0. In the next time step is going to be 0, 1, and then you're looking at a slightly different pixel. Perhaps you're looking at the same pixel. And then another one that's further away. And so think about this thing here as tracing a path on the sky. Every row has just zeros, except one at a single position. If it's polarization, then it's slightly more difficult, but let's forget about that for now. For temperature, it's just one in the pixel that you're hitting. And this is a very convenient representation for describing the observation path of the telescope. And so what we do now is we put that up here, pointing TOP, and now we recognize that these sky maps are also pixelized. So that has an index P there. And this matrix here also has a pixel index. So these things here can vary on the sky. I can put that here, beta or P. So now, what this describes is essentially an observation path on the sky with the pointing matrix. So that is the pointing matrix. Fortunately, that is usually pretty well known. I mean, we are, at least for the current satellite experiments we are working on, this has been really well defined by star trackers and things like that. So we don't need to estimate that. But we have worked on ground-based experiments where all of this has been done. Okay, and that brings us now to after the photons are going through the instrument or the telescope, they are in the detectors, and they need to be amplified. And that's where the gain is coming in, G of T. And that's the amplification factor as a function of time, because the G in itself can vary in time. So, sky signal going through a bandpass, a beam, a pointing matrix, and a gain. That's a pretty good description for, say, the Planck LFI sky signal. And we have now unknown gain here, and we have the pointing here, the beam, and the mixing matrix, and the bandpass in there, and the sky maps. Maps there. Okay, so now we have a more realistic data model, capturing a lot of the important stuff here, plus noise. But we're not done yet, because there are some additional other terms as well that comes into play. For instance, this beam thing here, usually in this model here, we're looking at pointing matrix here, we're just saying, okay, which point is the telescope looking at right now? But some of the signal is actually coming through what is called side lobes. So that is essentially light coming, if I'm pointing over here, some light is hitting, say, the secondary or throughout the main path and being scattered into the detectors. So that is what is called side lobes. And that is depending on the sky signal as such, but also on the rotation on the telescope. So it's not the same, even though I'm pointing here, it's going to be different whether I'm looking at the telescope up or sideways and another way around like that. And for mathematical convenience, it's often useful to pull that out as a special term that is time dependent. FSL as in far side lobe. And this is going to be frequency dependent and it's going to be time dependent. So that is one term that mathematically you can get by scanning this thing here with the beam and pointing matrix, but pull it out as a separate term because it's essentially a nuisance term that we don't want to let leak into this term here. We want to shield this one by subtracting it. So we're keeping that as a term. There are other terms as well. An example of that is S zodiacal light, which also is frequency and time dependent. And this is light coming from our own solar system. It's dust within our solar system. And that means that this is not stationary. It depends on which position you are in around the sun, which time of year it is essentially. And so that also doesn't fall naturally into the signal here, and needs to be handled as a separate term. A third term that is really important is what is called correlated noise, N-core. And that is essentially associated with this thing here. So the gain thing here is fluctuating very rapidly. It has what is called a 1 or F noise spectrum. And that in itself, if there is an offset in the system, it's going to modulate that and it creates something that looks like an additional term here. So what it looks like intuitively is that the noise term, if you're just looking at the instrument as a function of time, you have something that looks like this. It's random, it's Gaussian typically, but it has a non-trivial correlation structure in time. It's correlated. For comparison, the white noise term here is really uncorrelated time, so that is like that. So the sum of the two is going to be this thing here. And that's a total noise term. So yeah, the correlated noise term is really important for most of these experiments. and that's something that Håvard will be coming back to in a future session. But yeah, now we have a data model that is, okay, let's write this up, side lobes. zodiacal light, correlated noise, light. Okay, so now we have a data model that we can actually work with, and for Planck LFI, this appears to be doing a really good job. In fact, even without this one. The zodiacal light is so weak that we don't really have to worry about that for now. So this is currently what we're working on for Planck LFI. So we have a complicated data model. The three parameters are gain. You might have some mean, we don't have support for that yet, but that's coming soon, I hope. Bandpass uncertainties, 4 band spectral parameters, amplitude maps, that's a ring around the unknowns. This and that and that. And well, this is a deterministic correction factor given by this, so we don't need to direct with that. This is a stochastic variable, and that is some leftovers, so to speak. And now we want to then sample the probability distribution of all of these parameters given the raw time-ordered data. So we want to sample from P of, okay, then just like, let's write them down. G, comma, B, beta, the amplitudes, delta bandpass, N core, given data from, say, LFI, for instance. This is the posterior distribution that we really care about. If we want the cosmological parameters, we could do that inside here, but that would only depend on the C and E type here, so that's something that can be treated separately. For now, let's think about this one. And the goal now is, let's set up a sampling algorithm for how to draw samples from this probability distribution. Again, drawing from a joint distribution like this is really difficult. We have no idea how to even start on doing that. But this is where Gibbs sampling again comes to the rescue. So let's write down the following Gibbs chain. Okay, the first step is P of G given data beta A delta N core. So I'm going to draw G of I plus 1 from that distribution. Then I'm looking at beta I plus 1 from P of beta given B A delta N core, and then G I plus 1. And here is I. And here is I, and so. So now all of these are the previous iteration, and this has now been updated to the new one. Then we have the amplitudes. AI plus 1 is drawn from P of A given D, delta I, N core I plus 1, G I plus 1, and then beta I plus 1, and so on. If you want additional parameters in your data model, you add another term like this, keeping all the other parameters fixed and only care about the other one. But then once you've done that, you have to remember to feed the new sample into the estimates of the other ones. So that's how generalization of this framework works. Yeah. So, of course, each of these steps here correspond to one important correction step in its own right. Like this thing here, for instance, this is essentially, these two are component separation, usually known as component separation. Gain estimation, that's another big part of any CMB experiment. Here it's all integrated into one iterative chain. And yeah, correlated noise as well. We can write that down in core. I plus 1, P of N core, I given D and everything else. Why don't we talk about this? Essentially there will be one lecture per step here from what the most important ones, so you can see what this actually means in practice. How do we draw a sample from each of these steps? And that will hopefully then also give you some understanding of how this works, what takes time, what are the challenges, how can we generalize it, and so on. So that's going to be topics for the next sessions that are coming up shortly. Thank you so far, and I'll talk to you all soon.